My name is Maciej Bednarczyk. I'm a robotics research engineer at iCube, and I will speak about EtherCAT module and ROS2, which will be an extension of what Dennis was explaining. So it's perfect, perfect in timing. So just a quick shot on who we are. So I'm coming from the iCube laboratory in Strasbourg in France. So it's a big laboratory where we do a lot of engineering, computer science, imaging science, and so on. So we are a great great and size research unit, and we have a lot of teams in different departments, many people. So basically all the engineering and research and R&D like in the university part is done in iCube. And we work a lot with industrial partners, so on our research projects and with industrial partners also on many different fields like computer science, imaging, robotics, photonics and mechanics and so on. So the lab when I'm coming in particular is the Robotics Lab, and we specialize in medical robotics, but this is like our main application, especially minimally invasive surgeries and robot-assisted surgical procedures, and also rehabilitation robotics. And we are a kind of big team in robotics, and we cover a lot of different fields from mechanical design through system control, system integration, until the application at the end. And one of our goals is to provide support for research, to develop platforms, and then to facilitate the transfer of these parts into industry and companies. For this reason, we need some high-performance, reliable, and flexible tools, especially in terms of communication standards, as we want to do a lot of integration in many components. For example, custom-built systems, as you can see here. With, for example, the endoscopic part, or industrial robots that we can simply buy. For example, we use KUKA Iowa robots in this case. And so we need communication standards that then we can use across all these different components to build in a fast way our application, but with standards that are very easily then transferable into industrial products. So that is why we focused a lot of effort onto Fieldbuses. So they allow us to have a communication system with many components, which is industrial standard, and it allows us to create local networks, interconnecting a lot of different components. So some of them we buy from companies like robots, and some of them that we develop out of custom modules that we put together. The main advantages of doing so, it allows us to do a lot of cost reduction because it also reduces the cost of maintenance and installation of additional modules. It allows to extend the systems that are developed, and allows to have a better performance and a great interoperability, as these Fieldbuses in most cases are completely independent of the manufacturer that will provide the components. And also in the cases of complex system, it is very interesting as it allows the size of our data acquisition system. So for example, if you would have a classical actuation unit made of a link controlled by a motor and some sensors, here in this case you would need at least 3 channels to be able to control your system. So you would need 3 I/O systems one I/O system to control this actuation unit. But in complex system like robots, you would have different actuation units, and then you multiply a lot the number of connections that you would need. For example, in 3 systems out of 3 components, you have an enormous amount of data and of control channels that you need to take care of. And the use of these Fieldbuses allows us to basically have one acquisition unit that is specialized in doing one different task, and then we can chain them together inside of our Fieldbus. There are many different types of Fieldbuses that we can use, but the one that we really are working with a lot is the EtherCAT Fieldbus from Backup Automation, because it is a high-performance system that is easy to use and is very widely used, especially in Europe in industrial products, and has a very flexible topology. So the main key features that made us use the EtherCAT Fieldbus is the fact that it is deterministic, in contrary to other Fieldbuses, and it allows you to guarantee the data transfer between the different units in a particular time. And so it's a system that is based on the master-slave architecture, and allows to do very fast communication with your system with real-time guarantees and communication up to 100 microseconds, because it is using the process on the flight system, which means that basically you have one single data frame that is running through your entire system, and the different modules will exchange the data on the flight with this data frame. It's a very proven technology which is widely used in many fields, in many robotic systems, in many industrial environments, and it has a wide panel of EtherCAT masters, which are in many cases compatible with real-time systems, and also it supports the CAN over EtherCAT, which is the COE. So in our case, we decided to go with one particular master right now, which is the IgH EtherCAT Master, because it has some guarantees that we in our applications wanted to have. It is a master that is embedded in the system, in the Linux kernel directly. It is designed for hard real-time applications, and it has a complete integrality. It integrates completely the EtherCAT protocol with additional features, for example, the advanced diagnostic features that you have. So basically, you are running your application in your system user space, and then you are communicated with a kernel model which handles all the communication with the data layer. And also a very important point for us is that this EtherCAT Master was under the general public license, the GPL v2, that allows us to use it. To use it in our systems more widely. Also, one of the features that we are interested in using this is the CANopen over EtherCAT, as it allows us to use the capacities of the EtherCAT together with the standards of CANopen and the communication protocols that are coming with this. Especially the fact that we can have these process data objects and service data objects that are implemented in the standard. So process data objects basically allow us to have a deterministic cyclic data exchange with our system. This is very suited for getting, for example, current positions, sending some target positions, velocities, effort, all the data that we really want to acquire in a cyclic and deterministic way. And also service data objects that are used, that are transferred via some mailboxing system, which are acyclic data exchange, and that can be triggered. For example, if you want to get additional information on the drive, or if you want to do configuration of your drive. What is very interesting also in CANopen is the fact that it is standardizing some device profiles, giving it some standard, for example, parameters, standard behaviors, and state machines, which, for example, I will speak about later a bit, which is very interesting for if you use motor drives, for example. Motor drives have a standard, CANopen standard, which means that independently of the manufacturer that will provide these drives, we have a common standard that we can address many components of the same family, basically. And finally, when we are using this kind of system, we want to not only be able to communicate with our drive or our component in a deterministic way, but we also want to have some guarantees in terms of synchronization with controllers. And in this case, we were a lot interested in ROS control, because ROS control is this framework that allows us not only to do this abstraction of different hardware, but also to have some controllers which will be attached to that hardware, and that have some guarantees, for example, in real-time control, and especially the execution, step-by-step execution of the different components on our system. And the abstraction layer that comes with it of the hardware allows us to have a very simple integration of our hardware and our controller, and we can very easily build these huge applications using standard components and standard controllers, and then we can focus on really building the application itself instead of spending a lot of time of developing basically the core functionalities of the communication with our system. So the goal that we had that was not available at the moment when we started is we were working many years with EtherCAT, and we had a lot of stuff working on EtherCAT, but it took a lot of time to deploy these applications, and we wanted to use the features of ROS control and ROS in general and EtherCAT and combine them together. in a way that we can very easily assemble applications. And that is why we developed the EtherCAT driver ROS2, which goal is to make the assembly of any hardware, EtherCAT hardware component-based systems very easily and in a standardized way. One of the goal was the capacity of doing runtime configuration of the EtherCAT network and on the different components that we want to put on them, so that if we, for example, want to add additional sensor, we don't need to rewrite some additional hardware to integrate it directly. We can do directly the runtime configuration of our EtherCAT and make these additional components integrate directly into our system. We want to have a very user-friendly slave configuration method for our system and no source code modification. So basically all the runtime configuration is done using parameter files that we can just set up at startup. Our system is a plugin-based module design that is pluggable into ROS control directly as a hardware abstraction, and it is currently interfacing with the IgH EtherCAT Master and uses ROS2 control parameter files to set the entire system up. So in this context, we developed the driver itself, but also we developed generic plugins to be able to interface with different slave components for EtherCAT. So the main component of our framework, beside the ROS2, let's say, binding wrapper, is the EtherCAT generic slave, which is the generic plugin to configure and interact with EtherCAT slave component, and to do the state machine management, to start up and configure using the SDO to configure the module itself, and then do cyclic data exchange using PDO. So in our current architecture, we do, for example, the configuration is done on every time we do the activation of the hardware using the lifecycle management of ROS2 control. And then when the system state is in active mode, we trigger the PDO data exchange with the system, which allows us to get the data on the flight and then bind these PDO data into ROS control directly. We also provide SDO cyclic support using external services. So this is this time outside of ROS control. We provide a service server that allows you not only to, so the SDO is not only used to configure once the module, but you can use it on the flight while your PDO is running. You can then use this mailboxing system from a ROS service that time when you can get additional data, or you can do some modification of your configuration, basically everything that you could imagine. The increment of this was the specification of using motor drives. Motor drives have this norm, which is the CAA 402 norm, which is a CANopen standard. And we developed an inheritance of the previous controller to deal with particular constraints of these drives, especially the slave state management, machine management, which is a kind of particular. And to do so, we added this component, which is fully integrated right now in our framework. And I will show you how to set up this, for example, in the system. So if you are familiar with ROS control, or not maybe, you can see that basically to load a hardware in ROS control, you just use an additional component in the URDF file. So here, for example, you say that the hardware that you want to use at that specific point is the EtherCAT driver. So basically, if you would have a KUKA robot, you will have a KUKA robot driver. If you would have a UR, you will have a UR robot driver. In this case, you specify that the system you want to communicate with is the EtherCAT driver that allows you to connect ROS control with your EtherCAT master. Once you do this, you are able to specify for each different component, for example, here a joint of the robot, you are able to specify the EtherCAT modules that are associated with this particular component. So here we are speaking about joints, but you can do the same with sensors, and you can do the same with GPIO components in order to fit your robot description in URDF. And what you are declaring here is that you have these different state and commander interfaces, which are something which is specific to ROS control, which allows you to communicate between ROS control and your hardware to transfer the data, either to send commands to the system or get information from the system. And in this case, these state interfaces and command interfaces will be connected together with this EtherCAT slave module, and you have they will basically run this particular driver for motor control and upload the data higher into ROS control to use classical controllers and so on. You also can see that this driver is generic, so it applies to all CIA 402 controllers, but not all controllers behave, the drivers not behave the same. That is why you have a specific configuration file, but this time this configuration file is just a YAML file that you will load at startup on your system. And what will happen, so I will spare you the exact features of this, but this is a configuration file that you can upload to your system. These different components are basically what you will get out of the dock of the drive itself, and you can set it up here to make the connection with all the rest of the different components. But in general, what you have the main slave configuration, you have the service data objects that need to be uploaded to configure a drive at startup, and then you can set up your different receive and transmit PDOs, so process data objects, in order to communicate directly with the higher level, which is ROS control in this case. And here, as you can see, the binding between the states that you declared in URDF and the different drive components, which is, for example, this register here is the actual velocity of our motor. Basically, you declare it here using the state, binding them by name together with what is the URDF. And that is it that you need to do. And what we provide, for example, in one of our Git repos is pre-configured drives for different components. Here, for example, we have some pre-configured Maxon, Technosoft, Schneider, and Elmo drives, configuration files that you can use to start working with if you want to deploy it on your systems, and then you can start from there to modify them to fit your needs. Once you did this, you are ready to go. You have full features of ROS control, and then you can use classical ROS2 control controllers, for example, to do your position, trajectories. You can bind it and move it to generate path, for example, velocities, effort, and yeah, basically then you do the rest of the piping with classical ROS tools. Some examples, why do we do this? For example, in our cases, we build medical robots. And in these medical robots, we have, for example, here a robotized endoscopic system and a master control unit where the surgeon is sitting and performing the operation. And in this case, you use the EtherCAT driver with two master systems in order to communicate, to create one robot, so to create the robot and create the master interface and bind them together on ROS controlled in order to do the control of everything. Another case is made together with our KUKA driver that we developed. And to do, for example, in this case, we do soft material additive manufacturing under constraint. And for this, we use the features of MoveIt together with the driver of the KUKA robot that we developed and the EtherCAT driver to control the extrusion unit of our system. Everything is integrated into ROS control and behaves. So these are different systems using different communication channels, but are put together into one single application, which from the user perspective is basically one single robot, even if the different components are completely independent. Here you can see we also have a tracking unit, an optic tracking unit. This also, we developed drivers for it to integrate it into ROS control, and basically we can then put all the sensors, actuators, robotic system, EtherCAT buses together into one single component based on standard hardware, which can be configured directly on the flight without the need of adding additional things. And the advantage of using it that way is, in contrary, if you would have nodes, particular nodes, all the different components are well synchronized together. Finally, what's more for the fun part, but basically you can develop your own EtherCAT components based on, for example, Arduino with EtherCAT shields. If you have this, you can set up your, in the same ways that you would set up, for example, a motor drive, you can configure your Arduino to be able to use EtherCAT to communicate with your shield and, for example, get data here from a force sensor. Finally, our solution that we propose here was integrated into several industrial use cases, and I can show you one of them, which was developed for a French company, which is Weez-U Welding, which is developing a cobot for welding applications. And the control of the different joints here is made by using the EtherCAT driver that we provided and the generic plugins for motor controls. Oh, sorry, it's not running. So if you have a doubt, the robot is moving. So currently we have a stable version of our driver, which is the 1.2 version, which is running on ROS2 Humble, and we are working on testing and porting into ROS Iron also. We have a support for classical EtherCAT modules that I showed you, but also the CIA 402 EtherCAT motor drives. And in some cases, for some applications, in fact, the fact of using the IgH EtherCAT Master, it's kind of constraining for some people because you need to have a dedicated EtherCAT card, for example, that is bounded by the system. You need to run your component in the kernel space of your machine and so on. So that is why we are working currently actively on abstracting the master driver and being able to exchange the master that is using. So right now it's using EtherLab, so the IgH master, but we want to use also the SOEM EtherCAT master, which is another open source master, to be able to exchange these different masters depending on the need that you have. And this abstraction of the master will allow us also to do extensive testing and CI together with ROS2 control to have the compatibility at any time and use it maybe also in the rolling version. Currently, we are also working on additional error handling and recovery. What happens if, for example, the drive is failing? What will happen? What will it trigger if you have 6 axes on your motor? If one is failing, what do the others, and so on? And for this, we are working a lot on the lifecycle management, for example, for the CIA 402 drives, being able to change the state of the drives in the same time that you change the state of the ROS2 control hardware. And this is so that it behaves as a robot, for example, a classical robot. So at the end, what we really want is having, for example, a system built out of EtherCAT drives that is managing the life cycle state machine in the same way the ROS control, and then you can trigger, for example, the different states, react to fault, and so on. Okay, so if you are more interested into what we do, here you have a QR code to our GitHub repository where you can find the documentation also and some additional information about what we do and about how the driver is working. And and if you're interested in talking about this further, we can meet in the coffee and so on. And thank you very much.
Okay, thanks. So we have time for 2 or 3 short questions. Well, always the same one. Anyway, and you make a start, and maybe other ones follow.
Thank you very much. As a user of both ROS2 control and the EtherCAT driver, Ross, thank you for the work you've done there. And if this gets too technical, we can take it offline for lunch. But what I'm wondering is the architecture that you have with the slaves are that there's slaves as part of the component. So for one joint, you have an EtherCAT slave. For one sensor, you have an EtherCAT slave. But some robots that have EtherCAT drivers, like the Mechademic Mecha 500, they're the whole system already available through EtherCAT. And for those, we couldn't find a good way to use ROS2 control and these joint-based plugins with the generic EtherCAT driver. So we had to kind of write our own hardware interface for that. Do you have any thoughts on how you might be able to address those kind of systems in a ROS2 control architecture with a more generic driver?
So the thing that is, so in fact, currently, if you have many, for example, several joints on the same module, it's not, let's say, the way that the system that we developed is made like this, but 2 possibilities are available. Either you can, in fact, create your system as a GPIO with the different states that are coming from the different components. So this is one way. Secondly, if, for example, depending on what module are you using, but in many EtherCAT modules, you can separate different PDOs that are linked to separate to different joints that you would have, for example. And there is, in many cases, you can basically call several times the same module as with a particular plugin. Meaning that as long as you don't write on the same PDOs on the same time, there is no problem of having 10 instances of the same drive connecting to the same component, because what's happening under the hood, it's that the buffer is common, the data buffer. So if you have 10 modules that are writing on the same data buffer, as long as you don't like overlap the memory points, there is absolutely no issue. So in some cases, in fact, we do this. It's not the most elegant way, but for now, with what we have.
Okay, thanks. I think we have one more question.
A short one. So you mentioned that GPL is used. Isn't this a limitation for the integration with the proprietary applications?
It's a good question. So licensing part, yeah, it's not my job, I'd say. So for now, what we are using is this GPL license because it allows us to use it in our prototypes and then transfer it further. There are other, for example, that's also one of the advantage of using the SOEM, because the SOEM has also a commercial license. So it's free, but if you want to use it in a commercial product, you can also. So that's why we want to do this hardware abstraction, this master abstraction layer.
Okay, so any further questions? Yes.
A very short one.
I take your word.
So will you release a tracking system driver for ROS2 control?
For the one that I was speaking about,
Yes.
it's already released.
Ah, okay.
We have a support for NDA systems and OptiTrack systems.
But you didn't put it there in the list. Are you running this on a separate computer,
No,
or
it's on the same computer?
it's basically
on
in the same
computer in the same. So depending on the application, we can run it even in the same ROS control loop. This is used if we want to do, for example, visual servoing and so on. This is very important to have everything synchronized together. So that's why we are running it like on the big machine, but everything together.
Okay, thanks. So then let's thank our speaker once more. And